Welcome to the second session of the DVL webinar series, and thank you all for attending. Good day to all of you. My name is Wilbur Rattoni, and I am one of the field service engineers here in Teledyne RD Instruments in Poway, California. Today we will be talking about bottom tracking and water profiling with DVL. And yes, contrary to some beliefs, you can also use your DVL to collect current profiles. And before we start, please pay some attention to this slide on how to get in contact with us for either 24/7 technical support or for sales inquiries, either by phone or by email. There's also our website, which is a great resource for you to get basic information about the different DVL products, and some technical notes or papers written by both RDI and various DVL users, and some technical tips as well. Please note that depending on where you are in the world, we also have our office in Europe. They can be reached at the phone number and email address shown in this slide. In addition, we also have various offices worldwide available to support you depending on where you are in the world. For instance, aside from Europe, we also have our office in China and Brazil, and of course in the USA, which is where our headquarters is. Okay, so let's start. So, in the first session of the DVL webinar series, we've learned that our DVL can measure several entities, such as speed over ground and speed through water, and it can also collect current profile, can measure altitude, and many others. Today, we will be focusing our discussion on three items. Number one, bottom tracking or speed over ground. Number two, water tracking or speed through water. And number three, current profiling. Let's talk about bottom tracking first. So first of all, how do you obtain and install the bottom track feature in your DVL? Or let's say, who do you contact if you want this feature added or installed? Well, the good news is there's nothing that you have to do to obtain the bottom track feature, because bottom track comes as a default or standard with DVL, meaning once you receive your DVL, just power it up and you're good to go. But where is bottom tracking really used, and why is it important? It is important because it makes the measurement of speed over ground or speed through water, altitude or range to bottom, or distance made good, among others, possible. In the following slides, we will try to understand what makes bottom tracking work and how it is best optimized for various situations or sites in which your DVL is deployed. This slide shows you a picture of the most basic difference between bottom tracking and water profiling, which is their transmit pulse. In this picture, the bottom track transmit pulse is the green pulse, while the water profiling transmit pulse is the pink pulse. As you can see, a bottom track transmit pulse is much longer in length than a water profile transmit pulse. The water profile transmit pulse is approximately equal to the depth cell size, whereas a bottom track transmit pulse is approximately equal to 30% of the altitude. But the question is why? Why does the bottom track transmit pulse have to be that long? Why can't we just send a regular transmit pulse similar to a water profile transmit pulse? This picture compares a short pulse, which is the one on the left, versus a long pulse or a bottom track pulse, which is the one on the right, as they hit the bottom. To answer the question from the previous slide, the reason why bottom track pulse is or why bottom track pulse use long pulses is to allow the sound beam to insonify the bottom over the entire beam all at once. But again, the question is why? Why do you need to insonify the bottom over the entire beam all at once? Well, by illuminating the bottom across the beam all at once, a long pulse produces a more accurate and stable estimate of velocity, more accurate than is typically obtained from water profiles. This slide shows a simple animation comparing the echo intensity produced by a short pulse versus a long pulse. Please pay attention also to the graph on the right of your screen and notice the echo intensity produced by each pulse. Here's for the short pulse. And here's for the long pulse. As you can see, with a short pulse, there is an ambiguity in the bottom detection, which would make us less certain whether what was detected was really the bottom or just some ordinary volume backscatters. Whereas, with the long pulse, there is a more defined echo intensity and thus a more defined or certain bottom detection. This picture shows what goes on from the time the DVL transmits a bottom track pulse up to the time it receives the signal back. Let's imagine that a DVL just transmitted a signal, which is represented by this almost square signal here. The signal would then travel through the water column and meet some backscatters, which is represented by the crooked lines in this picture. Eventually, provided that the bottom is within the DVL's range, the transmitted signal would hit or detect the bottom, which is represented by the large bump or the second almost square signal in this picture. But the question is how? How exactly does the DVL really know if what was detected was really the bottom and not just some volume backscatters? In this slide, let's imagine we have this DVL. We will then let it transmit a bottom track pulse, and at the same time, let's monitor the strength of the return signal or the echo intensity as the bottom track pulse hits a target. Again, the signal would travel through the water column and meet some backscatters. From the previous slide, remember that at this point, there's a bottom detection which was represented by the strong return signal or the almost square signal. And so the question was, how do we know that it was really the bottom that was detected and not just some ordinary backscatters? Well, there's this parameter which is also user settable called the BA, or the bottom amplitude threshold. But what is this BA parameter? The BA basically sets the bar for an acceptable return signal's echo intensity expressed in the unit of counts. Anything above it is considered good and accepted, and anything below it is considered bad and rejected. There's also this parameter called BC, or bottom correlation threshold. And what does this BC parameter do? BC examines how well the return signals correlate with each other. How well the two signals correlate with each other is also expressed in the unit of counts. For example, let's say a target has been detected. How do we know if this is the bottom? Okay, let's imagine that the DVL signal hit a target and produced this kind of return signal, represented by the purple signal. As you can see, This signal fell below the threshold set by the BA parameter, which means that the DVL will know that this is not the bottom and thus would reject it. Now, imagine that the DVL signal hit a target and produced this kind of signal, represented by the red signal. As you can see, the signal exceeded the BA parameter. However, it does not meet the requirement set by the BC parameter. Now, imagine that a target produced this kind of signal, represented by the blue signal. As you can see, the signal exceeded the BA parameter, and also, they met the BC threshold, in which case, the DVL would consider this as a valid bottom detection and would use this data in its calculation. There are several bottom modes available for bottom tracking. Each bottom mode is specifically created to meet a specific situation or site where your DVL is deployed. So, depending on where your DVL is operating, you should select the bottom mode that best fits your scenario or site. In the following slides, we will explore the different modes and find out what makes them unique from one another. This table is a summary of the different bottom modes available for the DVL. These are bottom mode 4, bottom mode 5, 6, 7, and 8. Bottom mode 4 is the oldest mode. Bottom mode 5 is an improvement over bottom mode 4, most especially when it comes to operating in lower altitudes. It is also the default bottom mode for a DVL. We then took the lessons we learned from bottom mode 4 and bottom mode 5 and came up with a smarter bottom mode, which is bottom mode 7. Bottom modes 4, 5, 6, and 7 are all available for a workhorse navigator. There's also the most advanced bottom mode, which is available only in navigation engines, which is bottom mode 8. By the way, when I say navigation engines, I mean this. And this, on the other hand, is a workhorse navigator. With bottom mode 8, we took the lessons learned from bottom mode 4, 5, and 7 and came up with this bottom mode. Again, each bottom track mode must be used depending on the specific situation or scenario. In the next slides, we will try to go in and examine more closely each mode and what makes them unique from one another. Bottom mode 4 is generally used at higher altitudes. Note that typically, the bottom track transmit pulse length is about 30% of the altitude, and with bottom mode 4, the bottom track transmit length is automatically adjusted with altitude. The only drawback of this mode is its measurements has high standard deviations at lower altitudes. And based on this problem, meaning the high standard deviation at lower altitudes, we developed bottom mode 5. Bottom mode 5's performance in high altitudes is comparable to bottom mode 4. However, bottom mode 5 has a reduced variance in lower altitudes by using the pulse-to-pulse processing technique, and is currently the default bottom track mode of your DVL. With bottom mode 5, the DVL divides the site into two, the deep zone and the shallow zone. The definition of the shallow zone would depend on the workhorse navigator's frequency. For example, for a 300 kHz navigator, the shallow zone is defined as below 12 meters of altitude. For a 600 kHz navigator, the shallow zone is defined as below 6 meters of altitude, while for a 1200 kHz navigator, it is below 3 meters of altitude. Then we have bottom mode 7. Bottom mode 7 is similar to bottom mode 5, except that it is optimized for slow-moving platforms in low-altitude, high backscatter environments. However, unlike bottom mode 5 or bottom mode 4, Bottom mode 7 is an optional feature and does not come standard with the DVL. Just like bottom mode 5, bottom mode 7 divides the sight into two, the shallow zone and the deep zone. It defines shallow zone as approximately below 4.7 meters of altitude. And just like bottom mode 5, with bottom mode 7, the DVL switches to a different processing strategy once it reaches the shallow zone. It uses both single pulse correlation and pulse-to-pulse correlation pulse-pulse correlation. With this type of processing, the DVL is able to obtain a more accurate and quieter measurements at lower altitudes. The only drawback to bottom mode 7 is that it is only available in 1200 kHz Navigator system and that the platform speed is limited only to 9 meters per second. Here's a table showing the summary of the effects on the standard deviation as you go nearer to the bottom. Please note that the x-axis is the range or altitude in meters, while the y-axis is the standard deviation in centimeters per second. Now, imagine that you have a DVL descending to a lower altitude. As you can see, as the DVL approaches the bottom, the standard deviation goes higher. This is most especially true with the oldest bottom mode, which is bottom mode 4, which is represented by the blue graph. However, you will notice that with bottom mode 5 and bottom mode 7, which are the pink and red lines respectively, when the DVL reaches the bottom, because of the processing strategies that we implemented for these modes, the standard deviation is much better compared to bottom mode 4. Contrary to some presumptions, the lower in altitude you go, the more challenging it is for the DVL, insofar as maintaining a low standard deviation is concerned. But why is that? Perhaps the simplest or easiest way to explain this is by imagining having a flashlight and a mirror. If you put your face so close to the mirror and then turn on your flashlight, you'd get blinded. But the further you walk away from the mirror, even with the flashlight on, the clearer you'll see your reflection on the mirror. And then there's bottom mode 8, which is the most advanced mode, but it is only available in the navigation engines. The lessons learned from bottom modes 5, 6, and 7 were all applied to produce this advanced bottom mode. With bottom mode 8, a feeler ping is transmitted to find the bottom. The bottom is then found, and the Explorer DVL sets the transmit pulse to 30% of the altitude for each beam, based on the respective feeler info. This allows it to have a higher resolution bottom detection. Also, with bottom mode 8, the DVL becomes capable of transmitting multiple pulses with different lags, and perform what is called lag hopping, which is basically the process of finding the best lags for quietest measurement, one at a time, separately for each beam. This reduces the risk or effect of interference between the beam's transmitted pulses, and thus allowing for a much quiet measurement and improved standard deviation at low altitudes. In other words, this mode is smart enough such that it is capable of switching processing strategy from deep to the switching altitude and then to the shallow zone, which leads to smoother transition when changing a certain altitude to another, and which also leads to better handling of slopey environments. And before we leave bottom tracking and proceed to the next topic, it is also worth noting that the most noticeable and may cause trouble if not paid attention to is the difference between PD0 output data versus PD4, 5, and 6, particularly on how the ROV or platform's direction is outputted. With PD0, the DVL assumes that the DVL is always stationary and that it is the ground that's moving. For instance, if your vehicle is moving towards north, the DVL, when using PD0 data output format, would interpret this as if the bottom is moving towards south, and thus, if not paid careful attention to, would make you think that your vehicle is moving south instead of north. However, with PD4, 5, and 6, this is not the case. The DVL assumes that the bottom is always stationary and that the vehicle is the one that's moving. So this means that if your vehicle moves north, the DVL would know that you're moving north, and so forth. Therefore, this is something that you might want to take note of when programming your systems. So that was bottom tracking. And now let's talk about water tracking. So what is water tracking? Simply put, water tracking is a method of providing speed through water from a reference water layer. But when is water tracking used, and what is its importance? Well, water tracking is particularly useful when the bottom is out of the DVL's range, or if the DVL can't properly detect the bottom, due to, let's say, it's a soft and muddy bottom, or for some other reasons. So how does water tracking really work? We already know from the previous slides that the DVL calculates various entities, such as altitude, speed over ground, and other important information that your platform or vehicle needs using bottom tracking. We also learned that the DVL will continue to bottom track for as long as the bottom is within its range, or for as long as the DVL gets a valid bottom detection. But what happens when the bottom becomes out of range, which might be a bad thing when you're relying on your DVL for navigation? Well, this is when water tracking comes into play. When the bottom is out of range, water tracking allows you to create a water layer, which the DVL can track off of. Think of the water layer as something like a virtual or imaginary bottom. There are two basic commands or parameters to keep in mind when water tracking. These are BL and BK. The BL command basically sets a water mass layer. You can use this layer as a reference point when the bottom is out of range or is incorrect. There are also various guidelines to note when setting a water layer. For example, the user-defined water mass layer is used unless the minimum layer comes within 20% of the water boundary, or the sea floor. As the user-defined water mass layer comes within 20% of the boundary, the layer compresses in size until the minimum water mass layer is reached. When the boundary moves closer to the transducer, no water mass ping will be sent. You can put your water layer either on deeper depths or as close to the vehicle as you want. This is totally up to you. Some users put their water layer in deeper depths, as far away from the DVL as allowed by the BL guidelines. This is so they can avoid strong water currents and thus minimizing possible bias in the data. Some users put it close to the vehicle for some reasons, but when doing this, one must be very careful about the effect of water drag as caused by the vehicle. For example, if the ROV drags the water in a similar direction to where it's heading, obviously this might bias the velocity reading to 0. BK is another important parameter to take note of. And so what is BK? In this slide, we'll find out what BK0, BK1, BK2, and BK3 means. So, if you set BK to BK0, we're basically telling the DVL that we do not want to perform water tracking. We only want bottom tracking all the time. With BK1, We're telling the DVL that we want to perform both water tracking and bottom tracking all the time, regardless if we have a good or bad bottom detection. With BK2, we're telling the DVL that we want to perform water tracking only if we have a bad bottom detection, such as when the bottom becomes out of range, for example. With BK3, we're telling the DVL that we only want to perform water tracking and never bottom tracking, regardless if the bottom is well within range of the DVL. One of the most important features of DVLs is their ability to measure current profiles. As mentioned in the earlier slides, water profiling uses short transmit pulses to obtain vertical resolution. We will try to discuss in more detail in the next slides how water profiling is done. And please note also that water profiling is an optional feature for a DVL. In other words, the water profiling feature does not come standard or default with a DVL, unlike bottom tracking. So how does the DVL perform water profiling? As you can see in this simple animation, return echoes from the outgoing transmit pulse are time-gated and stored into the depth cells as the transmit pulse moves through the water column, resulting in a current profile. The depth cells here are represented by the colored stacks in this slide. Basically, the DVL divides the velocity profile into uniform segments, which are the depth cells, through a process called range gating. Perhaps the easiest way to understand how the DVL water profiles is through this picture. As mentioned, the DVL produces multiple segments called depth cells, which is represented by the rectangular rows in this slide. Just imagine that this depth cell is equivalent to a single old-style mechanical current meter, only that the velocity measurement in each depth cell is more accurate compared to the current measurement by a single mechanical current meter. This is because in a given depth cell, the current velocities are averaged within the entire depth cell, whereas a mechanical current meter measures current only at a localized point. We already know how the DVL performs bottom tracking, which is the DVL transmits a long pulse to track or bounce off of a bottom. So, how about water profiling? First of all, please keep in mind that when performing water profiling, the DVL makes two key assumptions. The first assumption is that objects that return signals are moving along with currents. When I say objects, I'm referring to the backscatters such as planktons. We can't be tracking off of objects that swim against currents, or that can swim faster or slower than the water current such as fish. The second assumption is that all the beams of an ADCP are measuring the same currents. Again, the second assumption is that all the beams of an ADCP are measuring the same currents. For example, if beams 1, 2, and 3 are tracking off of planktons, beam 4 can't be tracking off of fish. Perhaps the easiest way to understand how the DVL performs water profiling is again by imagining we have a DVL. And this DVL is equivalent to that of a cop or a police holding a radar gun. Only this time, instead of pointing the radar gun and monitoring speeding cars, he monitors the backscatters moving along with the water current. This is the same analogy as to how the DVL measures water current. And just like bottom tracking, water profiling also uses some parameters to determine whether a return signal is good or must be rejected. These are the WA parameter and the WC parameter. The WA command is the fish rejection threshold. This parameter is similar to the BA parameter which we discussed earlier with bottom tracking. However, the difference is that with WA or fish rejection, the DVL screens for echo intensities that exceeds the WA threshold. Anything that exceeds this threshold is considered bad and must be rejected. Anything below is considered good and included in the processing. Why is this parameter important? This parameter is important because we found out from the previous slide that one key assumption when doing water profile is that the objects, such as planktons, that return the signals are moving along with the current. But what if the DVL what the DVL detected was actually a fish or just other hard objects that are not moving along with the current, meaning they're moving at different speed and direction than the water current, just like what is shown in this picture for a particular depth cell. Obviously, without the WA threshold, we risk having bad or questionable data. There's also another key parameter when water profiling called WC or correlation threshold. WC is similar to the BC or bottom correlation threshold of bottom tracking, which we discussed earlier. Just like bottom correlation threshold, WC examines or compares how well the received signals correlate with each other. Here's a simple illustration showing what WC does. Again, imagine we have a DVL and we let it transmit a pulse, this time a water profiling pulse instead of a bottom track pulse. The pulse travels through the water column until it hits its target. In this illustration, we send a pair of identical pulses in the water with a specific lag in between them. We know that these pair of pulses will eventually hit a target, such as plankton, and would return to the DVL. So in a nutshell, the WC compares how well these two pulses correlate with each other. The correlation is again expressed in the unit of counts. If the correlation of the two signals exceeds the threshold set by the WC parameter, then the DVL would consider the signal as good. Otherwise, it will be rejected and would not include it in the processing. Here's how the DVL calculates the actual water current and at the same time, a simple example of what bottom tracking is used for. When water profiling, the current measured by the DVL is what is known as the apparent or raw velocity. This velocity basically is the real water current plus the vehicle speed. In order to calculate the real or actual water current, the DVL must remove the vehicle speed from the raw speed. Again, the vehicle speed in this case is simply the bottom track speed or the vehicle speed over ground. And that will conclude the second session of the DVL webinar series. And once again, today we covered 3 topics, which are the bottom track velocity or speed over ground, water track velocity or speed through water, and current profiling with your DVL. I hope you find this session helpful and informative. Again, my name is Wilbur Rattoni, and thank you all for attending. And once again, for technical support or if you're interested in obtaining some information about your DVL, here are different ways to connect with us. Thank you again, and I hope you all have a great day.